Take a look at these reactions. When an alkyne is treated with hydrogen gas, and a metal of the same type that we use for alkenes, nickel, platinum, palladium are real common, that triple bond is fully reduced. The two alkyne carbons become methylene groups, CH2. But there's a special catalyst called Lindlar's catalyst that stops this reduction at the alkene stage. The alkyne is reduced to an alkene, but the alkene isn't further reduced. And what makes this reaction particularly available is that it only makes the Z or cis isomer. And the third reduction makes just the E isomer or trans. Using completely different conditions, sodium and ammonia, an alkyne is reduced to an alkene with the trans stereochemistry. So here we have a pair of reactions that lets us choose the stereochemistry of the alkene we're making. This is really valuable in synthetic chemistry, where we may need to have only the cis or only the trans stereochemistry of an alkene we're making. To understand why these reactions occur, full reduction, partial reduction, cis stereochemistry or trans stereochemistry, we need to take a look at the reaction mechanism. I've drawn a surface here that represents one of the catalytic metals, nickel, platinum, palladium. And during the reduction reaction, we put hydrogen gas and the alkyne together with this metal. In the first step of this process, the hydrogen gas interacts with the metal surface. The sigma bond holding the hydrogens breaks, and the hydrogen atoms form weak bonds with the metal. In the second step, a molecule of alkyne comes along and coordinates with the metal surface. As that pi bond coordinates with the surface, it weakens, and a hydrogen atom can be transferred from the metal surface to one of the carbons. This leaves us with a double bond, a hydrogen attached to one of the alkyne carbons, and a radical at the other carbon. That carbon needs one more electron to have a filled outer shell, so it acquires a hydrogen atom. We just made a cis alkene because both hydrogen atoms were added to the same side of the pi bond. That's because both of them were associated with the surface of the metal and added to the same side of the pi bond that was associated with the metal surface. Of course, this alkene leaves the surface of the metal to join other atoms in solution, and the reduction process can start all over again. But remember, this alkene that we just made is reduced using the very same conditions. So as we make the double bond from the triple bond, it too subsequently gets reduced, which explains why we have methylene groups as the product. Using these normal reduction conditions, hydrogen and one of these metals, we get the fully saturated product. However, there are conditions that prepare metal surfaces that are active enough to reduce alkynes, but not active enough to reduce alkenes. And look at this mixture that makes this poison palladium. The metal is treated with calcium carbonate, lead acetate, and quinoline. These are three very different substances, but together in this combination, they alter the palladium surface just enough so it reduces alkynes but not alkenes. And, as I mentioned, this reaction is stereoselective. It makes only the cis stereoisomer. The two hydrogens added are on the same side of the double bond. When we want to make the trans isomer, we use very different reaction conditions. These reducing conditions have nothing at all to do with catalytic reduction. The first step in the reaction is transfer of an electron from sodium to the pi bond. This happens because having a filled outer shell confers special stability on an atom. Sodium metal, being in column 1, has a single electron in its outer shell. If that electron leaves, that shell is empty, and the filled outer shell becomes the one below it. So sodium plus 1 is particularly stable. The electron transfers from sodium to the pi bond. The result is an anion. One of the two carbons has a pair of electrons and a negative charge. The other carbon of the pi bond has a single electron. That anion is a very strong base, and in the presence of ammonia, it takes a proton away from ammonia. The result is an intermediate that has a double bond, and one of the double bond carbons has a single electron. It needs another electron to have a filled outer shell, so it reacts with another sodium atom. It makes an alkene anion. The carbon now has a filled outer shell, but it has a negative charge and is a very strong base. So, again, we see proton transfer from ammonia. So this reaction mechanism is all well and good, but how does it account for the stereochemistry? Well, take a look. Once this initial anion picks up a proton, it's an alkene with defined stereochemistry. And the two alkyl groups, ethyl here, would prefer to be as far apart as possible. This avoids steric crowding, so they adopt the alkene stereochemistry that's shown here, which is trans. That stereochemistry is maintained as it's transformed first into an anion and then into product. So there you have it. 3 different conditions for reducing alkynes. One that fully reduces the triple bond. A second reaction that makes the alkene from an alkyne with just a cis stereochemistry. And a third reaction that makes an alkene from an alkyne with just a trans stereochemistry. Taken together, these 3 reactions provide powerful tools for using alkynes in organic synthesis.